Good morning, friends. This is Professor Chaubey, Professor Chaubey's physics class. Professor A.k.chaubey, under the heading Physics Made Simplest. I am to discuss here again some topic of electricity. We have covered earlier the Ohm's law, etc., and now I talk about the law of resistances. Law of resistances, that is, I discuss series and parallel combination. Series and parallel combination of resistances. Means how the resistances, if we have more than one resistance, means 2, 3, 4, and we want to make some network, some circuit, how we connect them in series, what will be the total impedance, total resistance, what will be the total resistance if we combine them in parallel. So we will talk about the series and parallel law of resistance combination. So first I talk about the series combination. Means I have, say, more than two resistors, 2 or 3 resistances, then how you can combine them? So I put, say, 3 resistances, R1, R2 and R3 are connected such that the second end of the first resistance is connected to the first end of the second resistance, and second end of this resistance connected to first end of this. So this is called series combination. Means that the end of the one resistance is connected to the start of the other resistance. So this is series combination, and I connect this with, say, a ammeter, current meter. I connect this with a switch, and then I put here a battery, a cell. And I have a voltmeter to measure the voltage, maybe here. It can measure voltage here, it can measure voltage here. So that is the voltmeter you can connect. It can measure the volt here. It can measure the voltage here also. So this voltmeter is having multiple functions. This measures this voltage V1, this measures this V2, this measures V3. Means voltage across the resistances, and measures voltage across the resistances, and there is cell also. And this is the key, so we connect the key. So we connect this series combination, battery, switch, that is the key, ammeter, and all 3 resistances in series. We use the voltmeter, 1 voltmeter or multimeter sufficient to measure the voltage of all. So we know that this V total voltage is now, others are having small resistance, negligible. Ammeter is a low resistance, so no voltage drop, and the whole total voltage of V is across the resistances V1, V2 and V3. Say I is the current flowing in the circuit here. So I current is flowing throughout the circuit. I is the current flowing in the circuit. So it is common. Means I is flowing in the R1, I is flowing in the R2, the same current. So the IR drop is the voltage. That is V1 is equal to IR1. Similarly V2 is equal to, from Ohm's law, IR2. Similarly V3 is equal to IR3. Means voltage drop across this resistance is IR. I is the current, R is the resistance. This is Ohm's law. And voltage V is total V is equal to V1 plus V2 and plus V3. If R is the total resistance then we can write V is equal to IR. Same current I is passing through the combination of total resistance R. So V is equal to, means this voltage here, V is equal to IR. So means V IR is equal to IR1 plus IR2 plus IR3 and so on. You will cancel this I, which is the throughout common, and then you can get that from this simple Ohm's law, combination of resistances, we can get that R is equal to R1 plus R2 plus R3. So this is the series law of the resistances combination, that if you have more than two resistances or you have only two resistances, you want to connect them as I have shown in the diagram. This is called series combinations. Then the total resistance of all the resistances, you have to simply add the resistances. So this is the series combinations. R is equal to R1 plus R2 plus R3. Now we go to the next combination of resistances. That is called, say, parallel combination. Parallel means when first end of all the resistance is connected together and the second end of the resistance is connected together, it is called parallel combination. Means I have, say, three resistances such that all are connected, say, one resistance, say, here, the other resistance, say, here, another resistance, say, here. So this is R1, this is R2, this is R3. So three resistances shown in this way, where first end of this is connected together, means, so this is connected here, this one end A, the other end B. So one end of all resistances here at A, other end of resistance here at B. This is called parallel combination of impedances or parallel combination of resistances. Now what I do, I connect this also to a circuit, like, say, I have one ammeter, I have one key, say key to open, and then I have a battery, and then I connect it here. And now I have a voltmeter, which I measure the voltage here, this voltage V. I measure the voltage, this voltage is same here, B is common, all resistances. I measure the current here, this is the I current, and then current divided here in the different branches. So let I1 be the current in this branch, I2 in this branch, and I3 in this branch. So current divided in here, finally all current reaches here. So here I1, I2 and I3. So this becomes here again I. In earlier series law we saw the voltage law. We apply the voltage, total voltage must be equal to the voltage of individual resistances. Here we see the current. The current I divided into I1, I2, I3. So current I is equal to all the three currents in the branches, I1 plus I2 plus I3. Because I current is divided into three branches. And what is I? From Ohm's law. If V is the voltage here, say if R is the total resistance of combination then we can write I is equal to Ohm's law, V over R. I1 is equal to V over R1. I2 is equal to V over R2. And I3 is equal to V over R3. So these all the three currents, we use the current law, the total current is same. So V over R is equal to V over R1 plus V over R2 plus V over R3. So that is V is common throughout. It means if you cancel the V, what is left is 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this becomes law of parallel combination, that three resistances can combine like this. More than three, you can write similar equation. So you can get, if there are two resistances only, if there are only two resistances, we can write that 1 over R is equal to 1 over R1 plus 1 over R2, or R is equal to R1 R2 divided by R1 plus R2. So this is the law of parallel combination of resistances. In parallel, the resistances, two resistances are given by like this. This is R2. And so on. Now you can see, I can give you one important result, that if you have two parallel resistances, one is say high, means say about 1000. Other is say low, means 1 ohm. These two are connected in parallel. What will be the combination resistance? Then remember always that when high resistances are connected in the series, high resistances are connected with the low resistance in parallel, the resultant is even lower than the lowest resistance. You have many parallel circuits like this, the resultant resistance will be less than the lowest resistance. You have many resistances in parallel, say like this. Like this you can have many. This is 1 ohm, this is 10 ohm, this is 100 ohm, this is 1000 ohm. You combine four and find out result will be less than 1. Because this resistance, lowest resistance, is shunting all the resistances. So major current is passing through this, less current here. So this resistance actually, so equivalent resistance of parallel circuit will be even less than this. Because the current will not, minimum current will pass through this, maximum will go through this. So this is the nearly equivalent resistance. You can have example of this. When you have two resistances, say 1000 and 1, what is the resultant? You see, 1 over R is equal to 1 over 1000 plus 1 over 1. These two. What will be resultant? R1, R2 over R1 plus R2. So R will be R1, R2 over R1 plus R2. So that is R is equal to 1000 into 1 divided by 1000 plus 1. So 1000 divided by 1000, 1. So this is 0.9, less than 1, because it is 1000, numerator is more slightly. So whenever we have such combination of low and high, the resultant is nearly equal to the low resistance 1 ohm. So this becomes nearly say 0.9. So this is important conclusion. So whenever you have in the electronic circuits low impedance and high impedance, we don't combine the low impedance to high impedance. I can give you an example just for your knowledge that we have amplifiers, linear amplifiers, which have input impedance low. And many circuits we have high impedance, we want to amplify that pulse. We don't combine amplifier directly with the circuit because high impedance in parallel to the low impedance of amplifier gives pulse attenuated. So what we do? We use a circuit which is called pre-amplifier. That is the before amplifier that has got gain not more than 1. It is 1 or less than 1. So that circuit is for impedance matching. Means high impedance on this side matches high impedance, other side low impedance and low impedance. So impedance matching pulse is not attenuated. So this is very important. Parallel combination of resistances, very important for the many electronic circuits. So this is very important law for the combination of resistances. Parallel combinations, how to shunt the circuits. So parallel combination and series combinations. Well, you can have some other, one more law. What is the effect of heating the resistance? How? Means temperature increase. If temperature of resistance is increased, any resistance, how the resistance varies, that we want to see. And that just like the linear expansion, heat is a linear expansion of the metal का. At the same time, the resistance also, if resistance wire is heated, temperature increases, its resistance increases. And we define, just like we have linear expansion in the heat, here also resistance is that we write that if R0 is resistance at 0 degree Celsius, RT is resistance at T degree Celsius, then we can write change in the resistance that RT minus R0 is proportional to temperature, or it is proportional to R0, or fractional increase, you can say RT minus R0 over R0. That is the fractional increase of the resistance. This is the fractional. Means RT minus R0 is increased resistance, divided by R0 becomes fraction. How much? If R0 initial, what fraction increases? So RT minus R0 over R0 is proportional to temperature T. And RT minus R0 over R0 is equal to, here we have a coefficient that is called proportionality coefficient, alpha T, where alpha is proportionality coefficient. This was the proportional. So alpha is like that. Or RT, we can write from this RT is equal to R0, 1 plus alpha T. So this is the law of increase of resistance with temperature. As the temperature increases, resistance RT increases, like this rule. R0 is the 0 degree, or R0 is 1 temperature, and RT, or we can have in place of 0, 1 and 2, you can write R2 or R1, like that. So this is the alpha is the coefficient of, you can say alpha is equal to RT minus R0 over R0 into T. So alpha is the coefficient of resistance increase per unit temperature increase. Fractional change of resistance per T is equal to 1. RT minus R0 over R0 is fractional increase of resistance and T is 1 degree. So fractional increase of resistance per unit rise of temperature. That is simply alpha. So this is very important effect of the increase of resistance as temperature increases. Just like the increase of length of the wire or any rod with the temperature. So resistance also increases with temperature like this. This is the law of resistance temperature dependence. Now I see to the whether can I have one or two some problem or if possible, what type of problem. Let me see that, yeah, let me do some problems. Say, two coils connected in series have a resistance of problem. Two coils connected in series have two coils connected in series have a resistance of 18 ohm. Two coils resistance, when they are connected in series, have a resistance 18 ohm, and when connected in parallel have a resistance of 4 ohm. And when connected in parallel the resistance is 4 ohm. Find the value of individual resistance. Find the value of individual resistances. Means we have to calculate R1 and R2. Where R1 and R2 series combination is 18 ohm, R1 and R2 parallel combination is 4 ohm. So very simple, just we write say R1 plus R2 series. R1 plus R2 is 18 ohm, series combination. And what we have parallel combination, that we can write. And R1, R2 over R1 plus R2 is 4 ohm. This two things are given you. Now you can find out R1 plus R2 here is 18. So you can get R1 into R2 is equal to 4 into 18. This 18 comes here. So that means it becomes 72. Now what we do? We write R1 minus R2 whole square to get the value of R1, R2. Say R1 minus R2 whole square is equal to what we write? R1 plus R2 whole square, this algebraic equation, minus 4R1 and R2. This we can write. R1 plus R2 whole square is R1 square plus R2 square plus twice R1 Here is minus, so minus 2 remains, so this becomes equal to this. So this algebraic equation we can use to get the R1, R2. Well, R1 minus R2 whole square is R1 plus R2, so 18 square minus 4 R1, R2. R1, R2 is 72, so 4 into 72. So you can solve this. 18 square minus this becomes 36. 18 square minus this. So R1 minus R2 square is this. So R1 minus R2 is under root of this. So that becomes 6. So R1 minus R2 is 6. R1 plus R2 is 18. Now solve this. Add this together. Add this R1, R2, R2 cancels. So 2R1 is 24. 18 plus 6. So R1 is 12. So R1 becomes 12. And we have R1 plus R2 18. So obviously R2 is 6. So one resistance is of 12 ohm, the other resistance is of 6 ohm. So this not very complicated numerical, just simple combination, application of resistance law, both laws, series and parallel combination. This gives you resultant. So in this way you can solve some more problems just to have exercise experience. Say I try some other also is possible. Find the resistors, find the circuit current, find the circuit current. In the circuit shown in our circuit given. We have given a circuit here, what the circuit and find out the current. So we have a triangular shape here, 3 resistances, say 300, 330. So this we have 3 resistances shown here, A, B and C. This is 300 ohm, this is 300 ohm, this is 30 ohm. No, this is 300 and this is 30. And we have to find out the current in the circuit where battery is connected here. Here we have a battery of 2 volt. So find out the current I using Ohm's law. So what do? We take this resistance combination A, B and C such that we start say A, C and yeah. So A and C we take. A and C. And then from C we have resistance, this is R1 resistance, AC, and then we have C point and we have another resistance and we get a point D, and then we get another resistance we get a point B. Means AC and B, AC and B. In between AC, so this end, B and D, this end, we have this A, C and CB here. So, and we have say D and A also, say this A and D, like this, A and D and C and B. So this, you see, this two resistances here are, this also R, we will put later value like this. So we have a circuit like, we can, this triangular circuit, we have divided like this, that say, we have resistances as shown here. And we can do the total circuit resistance, you can find out. The resistors in the branch A, B, C are the resistors in the branch ACB. ACB, resistors in the branch, ABC, ACB, resistors in the branch ABC, ABC are in series. A, B, C are in series. This A, B, this resistor and BC, this are in series. And this branch this branch is in parallel. And this branch, because this is series, and this is in parallel to this, and this branch is in parallel with the branch AC. Sorry, I have, all these are 30-30. I don't know how I have it 300. All 30-30-30. Parallel, in parallel with resistance AC. These two are in series and they are parallel connected with here. So this AC, this point, this becomes this in series, and so this is in parallel to this. So just we get the combination. So total resistance R. Parallel combination of this series and this means how we get 30 plus 30. Then these two in series and this in parallel. So R1 into R2 divided by R1 plus R2. So 30 plus 30 plus 30. This becomes 90, 60 into 30. So we can solve this. This is our 20 ohm. So R is 20 ohm. Now what the current? Current is, you have 2 volts, so I is equal to V over R. So that is 2 over 20 ohm. So 1 by 10, that means 0.1 ampere. That is the answer. Means these three resistances like this we have these two in series, and then they are in parallel to this. So this I think is a good example of numerical. Similarly, you try to solve some other numericals. More, this depends upon the practice, how much practice you are doing. So like that. Well, you can do. I will take a separate session of numericals. Maybe next time when we meet. Today I can stop here, or maybe we start next time like Kirchhoff's law or Wheatstone's bridge, etc. So friends, thank you for listening.